Proxima Centauri sits just beyond our cosmic doorstep, a mere 4.25 light-years away. That sounds close, almost neighborly. But here's the problem. With our fastest spacecraft, it would take 30,000 years to get there. 30,000 years. That's longer than recorded human history. And Proxima Centauri isn't even a particularly distant star. It's literally the closest one we've got. So why can't we reach it? Why, with all our technology and ambition, does the next star remain impossibly far? The answer isn't what most people think. It's not about better rockets or bigger fuel tanks. The barriers we face are woven into the fabric of reality itself. Physics that doesn't bend, mathematics that doesn't negotiate, and distances so vast they make our fastest achievements look like standing still. Let me show you exactly what we're up against. First, let's talk about distance. Really talk about it. Because when we say something is 4.25 light-years away, that number doesn't register. It can't. Our brains didn't evolve to comprehend distances measured in trillions of kilometers. So, let's scale it down. Imagine shrinking the sun to the size of a period on a printed page, about 0.5 millimeter across. At that scale, Earth would be a speck of dust about 3 centimeters away. Neptune would sit roughly a meter out. Voyager 1, humanity's most distant spacecraft, would be about 2.5 meters from our tiny dot of a sun after traveling for nearly 5 decades. Now, at this same scale, how far away would Proxima Centauri be? 8 miles. 8 miles from that period-sized sun to the next star. Or think about it this way. A car traveling at highway speeds, let's say 60 miles per hour, would take 48 million years to reach Proxima Centauri. 48 million years of continuous driving through the void. Modern humans have only existed for about 300,000 years. Civilization as we know it has been around for maybe 10,000. The distance to our nearest stellar neighbor spans timescales that dwarf human existence itself. This is what 4.25 light-years actually means. It's not just far. It's cosmically, absurdly, impossibly far by any measure relevant to human experience. And yet, we've tried. We've built spacecraft. We've launched them into the darkness. Voyager 1 is currently moving away from the Sun at 17.3 kilometers per second. That's fast enough to circle Earth in about 40 minutes. It's been traveling for 47 years and has covered less than 0.25% of the distance to Proxima Centauri. At its current speed, it would take 73,000 years to reach our nearest neighbor, if it were even headed in that direction, which it's not. But Voyager 1 isn't our fastest spacecraft. That title belongs to the Parker Solar Probe, which achieved a staggering speed of 192 kilometers per second, nearly 430,000 miles per hour, during its closest approach to the Sun in late 2024. It's the fastest object humanity has ever built. And you know what percentage of light speed that represents? About 0.064%. Not even 1/10 of 1%. Even at that record-breaking velocity, the Parker Solar Probe would still take roughly 30,000 years to reach Proxima Centauri. 300 centuries. Longer than the entire span of human civilization. And that's assuming it could maintain that speed indefinitely, which it can't. The probe only achieves those velocities during brief flybys of the Sun, using gravity to slingshot itself faster. In deep space, far from any gravitational assists, it would slow down considerably. This reveals our first fundamental problem. We're not even remotely close to the speeds needed for practical interstellar travel. Not in the same ballpark, not on the same planet. We're playing a completely different game. So what would it take to make the journey in a reasonable time frame? Let's say we want to reach Proxima Centauri in a human lifetime. Call it 70 years. That would require traveling at roughly 6% of light speed. 6% might not sound like much, but we're currently achieving 0.064% at our absolute maximum. We'd need to go nearly 100 times faster than our fastest spacecraft has ever traveled. But wait, it gets worse. Much worse. Because speed isn't the only issue. The real nightmare is what it takes to achieve that speed in the first place. Enter the Tsiolkovsky rocket equation. This elegant piece of mathematics has governed every rocket launch since the dawn of spaceflight. And it's the reason interstellar travel isn't just difficult, it's essentially impossible with conventional propulsion. The equation tells us how much fuel we need to achieve a given change in velocity. And the answer for interstellar speeds is horrifying. Here's how it works. Every rocket carries fuel, but that fuel has mass. And to accelerate that mass, you need more fuel. But that additional fuel also has mass, requiring even more fuel to move it. You end up in an exponential nightmare where most of your fuel exists solely to carry other fuel that will be burned later in the journey. The spacecraft's useful payload, the actual stuff you want to transport, becomes an ever smaller fraction of the total mass. For a Mars mission, the fuel requirements are already brutal. A spacecraft needs a velocity change of about 20 kilometers per second, which demands fuel mass roughly 146 times greater than the spacecraft and payload combined. That's already pushing the limits of what's practical. But Mars is practically next door. For interstellar missions, the numbers become absurd. To reach Alpha Centauri in a century, allowing time for both acceleration and deceleration with a maximum velocity around 4.4% of light speed, you'd need a fuel-to-payload ratio that exceeds comprehension. We're not talking about thousands to one or even millions to one. The amount of fuel required would be 10 to the power of 2,200 times the mass of the observable universe. Let me repeat that. More fuel than exists in the entire observable universe, by a factor of 10, followed by 2,200 zeros. This isn't an engineering challenge. It's not something we can solve with better materials or smarter design. It's a mathematical proof that conventional rocket propulsion simply cannot work for interstellar travel. The universe itself doesn't contain enough matter to fuel the journey using chemical or even nuclear rockets. But maybe we don't need conventional rockets. What about more exotic propulsion systems? Nuclear fusion, perhaps, or antimatter drives. Fusion propulsion offers some hope. A fusion rocket could theoretically achieve exhaust velocities of 150 to 350 kilometers per second. far better than chemical rockets. They would dramatically reduce the fuel requirements. But dramatically reduce still leaves us needing fuel mass equivalent to tens of thousands of suns. And we haven't even successfully built a functioning fusion reactor for power generation, let alone miniaturize one for spacecraft propulsion. The 2022 breakthrough at Lawrence Livermore National Laboratory achieved fusion net gain for the first time. But the reactor is the size of a building and nowhere close to the compact, high-thrust system needed for space travel. What about antimatter? In theory, matter-antimatter annihilation releases the maximum possible energy from mass, converting it directly according to Einstein's famous equation. An antimatter rocket could potentially reach 50 to 80% of light speed. The fuel requirements would finally drop to manageable levels. There's just one tiny problem. We can't make antimatter in meaningful quantities. Producing even a single gram of antimatter would require more energy than entire nations consume in a year. Current production rates are measured in nanograms, billionths of a gram, and storing it without letting it annihilate with normal matter is another nightmare entirely. The cost of producing enough antimatter to fuel an interstellar mission would dwarf the GDP of Earth many times over. We're talking about an energy investment that makes building the pyramids look like a weekend DIY project. And here's the thing. Even if we somehow solved the propulsion problem, even if we discovered some revolutionary new physics that let us build engines capable of reaching significant fractions of light speed without requiring impossible amounts of fuel, we'd still face another insurmountable barrier, one that's even more fundamental than the rocket equation, the speed of light itself. Albert Einstein showed us in 1905 that the speed of light isn't just fast, it's the universe's absolute speed limit. Nothing with mass can reach it, let alone exceed it. As objects approach light speed, their mass increases, requiring exponentially more energy to accelerate further. At exactly light speed, any object with mass would have infinite mass and require infinite energy. Since infinite energy doesn't exist in our finite universe, nothing with mass can ever reach light speed. This means that even with perfect propulsion, even if we had unlimited energy and could ignore the rocket equation entirely, we'd still be limited to speeds below light speed. And at light speed, Proxima Centauri is still 4.22 years away. For more distant stars, we're talking decades, centuries, or millennia of travel time, even at the maximum possible velocity. Could we somehow break this barrier? Could we go faster than light? Every serious physicist will tell you the same thing. No, special relativity isn't just a theory we might overturn with new discoveries. It's been tested and confirmed in countless experiments. Particle accelerators routinely push protons to 99.9999% of light speed, and the behavior matches Einstein's predictions exactly. The mass increases, the energy requirements skyrocket. The light speed barrier holds firm. Some people point to exotic possibilities like warp drives or wormholes. These ideas exist in the mathematics of general relativity, but they require exotic matter with negative mass energy, something that's never been observed and may not exist at all. Even if it does exist, harnessing it would require energy scales at the Planck level, 10 to the 19th billion electron volts. That's a quadrillion times more powerful than our most advanced particle accelerators. We're not talking about advanced technology here. We're talking about manipulating the fundamental structure of space-time itself, something that may simply be impossible, regardless of technological advancement. The physics isn't going to change. The speed of light barrier isn't a challenge to overcome. It's a fundamental property of the universe we inhabit. So we can't build rockets powerful enough to reach interstellar speeds in reasonable timeframes. We can't break the light speed barrier. What about simply taking our time? What if we built enormous generation ships, vessels large enough to sustain human populations for thousands of years, with descendants completing the journey their ancestors began? This sounds like science fiction, and it is. But unlike faster-than-light travel, generation ships don't violate any laws of physics. They're theoretically possible. The question is whether they're practically feasible, and the answer, unfortunately, is probably not. A generation ship would need to be completely self-sufficient for centuries or millennia. It would need to grow food, recycle air and water, maintain complex machinery, and provide living space for potentially thousands of people. Based on current estimates, each person requires about 2 metric tons of consumables per year. For a crew of 1,000 people over a 250-year journey, that's 500,000 metric tons of supplies. And that's assuming perfect recycling, which we've never achieved even in controlled environments like the International Space Station. The ship would need to be enormous, not just large, incomprehensibly massive. It would require complete ecosystems, redundant life support systems, manufacturing facilities to replace broken equipment, and enough genetic diversity to avoid inbreeding over multiple generations. We're talking about essentially building a small, self-sustaining world and launching it into space. And here's the terrifying part. There's no rescue. If something goes wrong, if the life support fails, if a critical system breaks down beyond repair, if the ecosystem collapses, everyone dies. Unlike a lunar or Martian colony, where emergency supplies could theoretically arrive within weeks or months, a generation ship would be truly alone. Help would be decades or centuries away at minimum. The crew would need to anticipate and solve every possible problem entirely on their own. We've never built anything remotely close to this. We can barely keep people alive in low Earth orbit for a year without resupply missions. The idea that we could construct a fully self-sufficient biosphere that functions flawlessly for centuries is, at best, wildly optimistic. But let's say we somehow solved all these problems. Let's imagine we built a generation ship, launched it toward Proxima Centauri, and it successfully completed its multi-century journey. What then? The travelers would arrive at a destination chosen by people who've been dead for generations, based on information that's centuries out of date. They'd have no way to return, no way to communicate with Earth in any meaningful sense. Radio signals would take 4.25 years each way, making conversation impossible. And here's something most people don't consider. The ship would almost certainly be obsolete before it arrived. technology advances exponentially. A generation ship launched today at 1% of light speed would take 425 years to reach Proxima Centauri. But in those 425 years, technology on Earth would continue to develop. It's entirely plausible that a faster ship launched a century or two later would overtake the original vessel and arrive first. The generation ship's crew would spend their entire lives traveling to a destination that had already been reached by their descendants' descendants using better technology. This is the weight calculation problem, and it fundamentally undermines the logic of generation ships. Why launch a slow vessel when waiting for better propulsion might get you there faster? We're not even close to having the technology for generation ships, and even if we did, the practical and ethical problems might be insurmountable. You'd essentially be condemning multiple generations to life imprisonment aboard a spacecraft, with no choice in the matter, all for a mission they didn't volunteer for. So conventional propulsion doesn't work. Lightspeed is an absolute barrier. Generation ships face overwhelming practical challenges. What options does that leave us? In recent years, one project has captured the imagination of scientists and the public alike. It's called Breakthrough Starshot, and it represents perhaps our best hope for reaching another star this century. But as we'll discover, even this ambitious program faces obstacles that might prove impossible to overcome. Breakthrough Starshot emerged in 2016 with a promise that felt almost too good to be true. Billionaire Yuri Milner and physicist Stephen Hawking stood on stage announcing a $100 million initiative to send spacecraft to Alpha Centauri within a generation. Not centuries, not millennia, within our lifetimes. The concept is elegantly simple. Instead of carrying fuel, you'd use light itself as propulsion. Build tiny spacecraft, nanocrafts weighing just a few grams, and attach them to ultra-lightweight sails. Then blast these sails with an enormously powerful ground-based laser array. The photons from the laser would push against the sail, accelerating the craft to 20% of light speed. At that velocity, you'd reach Proxima Centauri in just over 20 years. 20 years, that's revolutionary. That's the difference between sending a probe your children might see results from versus one your distant descendants would inherit. The technology sounds straightforward enough. We understand solar sails. Spacecraft pushed by sunlight have already been tested in space. We know how to build powerful lasers. We're getting better at miniaturizing electronics. Combine these elements, and you've got a plausible path to the stars. Except nothing about Breakthrough Starshot is actually straightforward. Start with the laser array. We're not talking about a few powerful lasers. The proposal requires a phased array of thousands of lasers working in perfect synchronization, generating about 100 gigawatts of power. That's roughly the output of 100 nuclear power plants, all focused into a beam narrow enough to hit a sail the size of a bedsheet from Earth's surface. Building this array would require advances in laser technology we simply don't have yet. The individual lasers would need to be more powerful and more efficient than anything currently available. The cooling systems alone present enormous engineering challenges. You're essentially trying to prevent your laser farm from melting itself. Then there's the targeting problem. You need to keep this incredibly powerful beam locked onto a sail that's accelerating away from Earth at thousands of kilometers per second. The sail is tiny. The distances involved are enormous, and you need to maintain that lock for several minutes while the craft accelerates to its final velocity. Miss by even a fraction of a degree, and you've just wasted gigawatts of energy shooting a laser into empty space. Hit the sail off-center, and you might send your carefully designed spacecraft tumbling out of control. But let's say you solve the laser problem. Now you're dealing with the sail itself. It needs to be incredibly lightweight. We're talking materials measured in atoms thick. Yet it also needs to withstand temperatures that would vaporize most materials instantly. When 100 gigawatts hits your sail, even for just a few minutes, the material better not burn, warp, or tear. No such material currently exists. Researchers are exploring possibilities like graphene and other exotic materials, but we're nowhere near having something we could actually manufacture at scale and deploy in space. And remember, you're not building one of these. Breakthrough Starshot envisions launching thousands or even millions of these nanocrafts to increase the odds that some successfully complete the journey. The nanocraft itself presents its own maze of problems. You need to pack into a few grams everything required for a decades-long journey through interstellar space. That means sensors, cameras, power systems, communication equipment, and computational hardware, all built to withstand the extreme conditions of space travel at relativistic speeds. Consider the communication challenge alone. Your nanocraft is traveling at 60,000 kilometers per second. It's getting farther from Earth every moment. The power available to transmit signals back home is measured in milliwatts at best. You're running on a power budget smaller than a smartphone. Yet you need to send data across distances where the signal will take years to arrive, spreading out and weakening with every kilometer traveled. The math is brutal. By the time your craft reaches Alpha Centauri, its signal will be so faint that detecting it from Earth will require receivers far more sensitive than anything we've built. And that's assuming the communication system survives the journey at all. Which brings us to perhaps the most fundamental problem: durability. Your nanocraft needs to function perfectly for over 20 years in one of the most hostile environments imaginable. There's no maintenance, no repairs, no software updates. If anything breaks, the mission is over. In low Earth orbit, spacecraft regularly fail after just a few years, despite being much larger, better shielded, and far more robust than any nanocraft could be. The breakthrough Starshot probe would face radiation levels orders of magnitude higher, micrometeorite impacts at relativistic speeds, and temperature extremes that cycle between near absolute zero and scorching heat, all while maintaining precise orientation and keeping its delicate instruments operational. Then there's what happens when you're actually traveling at 20% of light speed. At that velocity, even individual hydrogen atoms, which float throughout interstellar space, become dangerous. They hit your spacecraft with enough energy to damage electronics and erode materials. The interstellar medium, sparse as it is, becomes a sandblaster operating at cosmic speeds. You'd need shielding, which adds mass. But mass is exactly what you can't afford when you're trying to accelerate with light pressure. It's another engineering trade-off with no clear solution. Protect your instruments, and you might be too heavy to reach your target speed. Skip the shielding, and your instruments might not survive the journey. Here's something most people don't consider. Even if everything works perfectly, you get exactly one shot at collecting data. Your nanocraft screams through the Alpha Centauri system at 60,000 kilometers per second. You have maybe a few hours, possibly less, to observe everything you came to see. Your instruments need to work flawlessly during that brief window, capturing images and data while traveling at a speed that makes orbital mechanics irrelevant. There's no circling back for another pass, no parking in orbit to conduct long-term observations. You're threading a needle at 1/5 light speed, grabbing whatever data you can, and then continuing on into the darkness beyond. And after all that, you still need to get your findings back to Earth, which takes another 4.25 years at light speed. So from launch to receiving the first images from another star system, you're looking at roughly 30 years minimum. That's if everything works perfectly. Which brings us to the project's current status. When Breakthrough Starshot launched in 2016, the excitement was palpable. $100 million, Stephen Hawking's endorsement, a clear timeline projecting first launches by the mid-2000s. Major institutions getting involved. It felt like humanity was finally getting serious about interstellar travel. 8 years later, the picture is considerably less clear. The frequent announcements have stopped. The multi-institution meetings have ceased. Scientists who were involved with the project express confusion about its current status. The funding that was supposed to materialize, that $100 million, appears to have fallen far short. One insider suggests the actual amount deployed was significantly less. What happened? The uncomfortable truth is that Breakthrough Starshot fell victim to one of the fundamental problems with relying on billionaire funding for major scientific endeavors. When the wealthy patron loses interest or moves on to other projects, the initiative can collapse regardless of its scientific merit. Yuri Milner has shifted focus to other ventures. Without his sustained attention and funding, Breakthrough Starshot exists in a kind of limbo. Some research continues. The technical challenges are being studied. But the sense of momentum, of inevitable progress toward actually launching these spacecraft, has evaporated. The project did identify something valuable, a list of approximately 25 major technological hurdles that need solving before Breakthrough Starshot could become reality. That list itself is revealing. It's not 3 or 4 big problems. It's 25 significant engineering challenges, each requiring breakthrough innovations in materials, science, laser technology, miniaturization, or propulsion physics. Some defenders of the project point out that nobody expected this to be easy. Interstellar flight was always going to require decades of development. The current plan stretches across 30 years, with the first decade devoted entirely to proof of concept work. By that measure, we're still in the early stages of figuring out whether this approach is even feasible. That's a fair point. But it also highlights the precarious nature of the endeavor. We're less than a decade in, and already facing funding uncertainty and questions about the project's future. What happens when the next major technical obstacle emerges? What happens when cost estimates inevitably increase? What happens when the timeline extends beyond the projected 30 years? The history of space exploration is littered with ambitious projects that seemed viable until they encountered reality. Plans that looked good on paper, but collapsed when confronted with the actual difficulty of building and testing hardware. Breakthrough Starshot may yet succeed, but its current trajectory doesn't inspire confidence. And even if it does succeed, even if every technical problem gets solved and we successfully send nanocrafts to Alpha Centauri, we need to confront what we're actually getting for this enormous investment of time, money, and effort. We're sending tiny probes that will spend decades traveling to another star system, collect data for a few hours during a high-speed flyby, and transmit that information back to Earth years later. No landing, no detailed exploration, no ability to study anything in depth. Is that worth $10 billion? Is it worth 30 years of development? Those aren't questions with obvious answers. The scientific return might be modest. A few images, some basic measurements, confirmation that planets exist around Alpha Centauri, if we haven't already discovered that through telescope observations. The symbolic value is harder to quantify. Proving that humanity can reach another star system, even with tiny unmanned probes, would represent a genuine milestone. It would demonstrate capabilities we've never had before. It might inspire a generation of scientists and engineers. But inspiration doesn't solve the fundamental physics and engineering problems that make interstellar travel so difficult. There's also the weight calculation to consider. Remember, Breakthrough Starshot aims to reach 20% of light speed. That's impressively fast compared to anything we've done before. But it still means a journey of over 20 years, plus another 4 years for the signal to return. That's a quarter century from launch to data. In 25 years, technology will advance dramatically. Detection methods will improve. Our telescopes will become more powerful. We might learn more about Alpha Centauri's planets from Earth-based observations than we would from a high-speed flyby. We might develop better propulsion methods that could send a faster, more capable probe. The people who launched the mission might find their data obsolete by the time it arrives. This is the paradox of interstellar exploration. The better our technology gets, the less sense it makes to launch with current technology. You're always better off waiting for the next generation of propulsion, sensors, or spacecraft design. Except if everyone thinks that way, nobody ever launches anything. Breakthrough Starshot represents our best current answer to this paradox. Don't wait for perfect technology. Work with what's theoretically achievable and start building it. Accept that the project will take decades and that you might not live to see the results. Recognize that better approaches might emerge later, but commit to this one anyway, because doing something is better than doing nothing. It's a philosophy born of impatience and ambition. Whether it's also practical remains an open question, one that won't be answered for years, possibly decades, if it gets answered at all. The alternative to waiting isn't just building better probes. It's fundamentally reconsidering what we mean by reaching another star. If you can't send humans, send machines. If machines are too heavy, send something lighter. If you can't build a self-contained spacecraft, build something that doesn't need to carry its own fuel. This chain of reasoning leads to an idea that sounds almost absurdly simple. Why carry fuel at all? Nuclear propulsion has been the default assumption for serious interstellar concepts since the 1960s. Fission, fusion, antimatter. The details change, but the basic premise stays the same. You bring your energy source with you. You accelerate by expelling mass at high velocity. You fight against the rocket equation's tyranny by finding fuel sources with better energy density. Except the rocket equation doesn't care about your fuel's energy density as much as you'd like. It cares about mass ratios. For every kilogram of payload, you need exponentially more fuel. The numbers become absurd quickly. A fusion rocket optimized for interstellar travel might need fuel masses equivalent to 82,000 suns to reach a meaningful fraction of light speed. That's not a typo. 82,000 times the mass of our sun just to accelerate a relatively small spacecraft. You can't cheat physics by finding better fuel. The rocket equation is merciless, so stop carrying fuel entirely. Use something else to push your spacecraft, something external. Light has momentum. Not much, but it's there. Push against enough photons and you can accelerate. This isn't theoretical. Solar sails have been tested in space. They work. The problem is scale. Sunlight pressure is weak. To get meaningful acceleration, you need enormous sail areas, and you need to stay close to a bright light source, which is fine for moving around the solar system. Less fine for interstellar travel, where you're moving away from the sun and its light grows dimmer with every kilometer, unless you bring your own light source. Not on the spacecraft. That defeats the whole purpose. Instead, put it somewhere that stays behind. A massive laser array, powerful enough to push a spacecraft to relativistic speeds, powerful enough to keep pushing for years, decades, however long it takes to reach cruising velocity. This is Breakthrough Starshot's core concept. Build a ground-based laser array. Build tiny spacecraft with enormous light sails. Fire the laser at the spacecraft. Watch them accelerate to 20% of light speed. Simple in concept. Nightmarish in execution. Start with the laser. You need something outputting around 100 gigawatts. For reference, the entire United States electrical grid generates about 450 gigawatts during peak demand. You're building a laser system that consumes roughly a quarter of America's peak power generation. Not for an hour, not for a day, for the minutes it takes to accelerate each spacecraft. That power has to be focused precisely enough to hit a sail that's meters across from thousands of kilometers away, while that sail is accelerating, while it's moving at an appreciable fraction of light speed, while atmospheric turbulence is distorting your beam. The targeting tolerances make threading a needle look like parking a bus. Then there's the sail itself. It needs to be large enough to catch meaningful amounts of light. It needs to be light enough that the momentum from those photons actually accelerates it. It needs to be strong enough that the laser doesn't vaporize it instantly. And it needs to be reflective enough that most of the light bounces off rather than being absorbed as heat. Current materials. Science can't build this. We have materials that are light. We have materials that are strong. We have materials that are reflective. We don't have materials that are all three simultaneously while also being manufacturable at the required scales. The engineering challenges pile up faster than solutions appear. Let's say you solve all of that. You've built your laser, you've built your sail, you've launched your spacecraft and accelerated it to 20% of light speed. Now you have a different problem. You can't slow down. The laser is back at Earth, 4.25 light years behind you. It can't help with deceleration. You're going to fly past Alpha Centauri at 70,000 kilometers per second. Your window for observation is measured in hours at best. Every instrument needs to work perfectly during that brief flyby. Because you don't get a second chance, some proposals suggest building a second laser at the destination to decelerate incoming spacecraft, which requires building interstellar infrastructure before you've achieved interstellar travel. The bootstrap problem becomes recursive. You need to send something to Alpha Centauri to build the deceleration laser, but that something needs a way to decelerate, which is what the laser is supposed to provide. You could split the sail, use part of it as a mirror to reflect the laser beam onto another part, creating a braking force. This halves your sail area, which means you need twice the laser power to achieve the same acceleration. The mass budget gets tighter, the engineering gets harder, or you accept the flyby. You design your mission around a high-speed pass through the target system. You pack your instruments accordingly. You make peace with the fact that your 30-year journey culminates in a few hours of frantic data collection, followed by an eternal coast into the interstellar void. This is what breakthrough Starshot is attempting. Not landing, not orbiting, not even a leisurely flyby. A glimpse, a snapshot, confirmation that we can throw something across interstellar space and have it arrive mostly intact. The cost-benefit calculation changes when you frame it that way. You're not exploring Alpha Centauri. You're proving a propulsion concept. You're demonstrating that light sails can reach relativistic speeds. You're testing whether nanocrafts can survive decades of interstellar transit and still function upon arrival. Those are valuable goals. They're just not the same as reaching another star in any meaningful sense. You're sending instruments past a star. That's different. But maybe that's enough. Maybe proving it's possible is the critical first step. Maybe you need to demonstrate the concept with tiny probes before you can justify building larger ones. Maybe breakthrough Starshot is the right flyer of interstellar travel. Crude, limited, but historically important. Except the right flyer led to incremental improvements. Each generation of aircraft was better than the last. The path from Kitty Hawk to modern aviation is clear. The path from nanoprobes to crude starships is anything but. Scaling up a light sail mission doesn't work linearly. Double the mass and you need quadruple the laser power. Add actual scientific instruments instead of minimalist sensors, and your power requirements explode. Try to include deceleration capability, and the mission becomes impossibly complex. The physics doesn't scale. That's the fundamental problem. Light sails work for tiny masses. They become progressively less practical as mass increases. There's no obvious path from we can push a gram-scale spacecraft to 20% of light speed 2. We can push a kilogram-scale spacecraft to the same speed. 2. We can push a ton-scale spacecraft. Each step up requires exponentially more infrastructure, more laser power, bigger arrays, better materials. The technology doesn't evolve smoothly. It hits walls. So maybe light sails are a dead end for anything beyond minimal probes. Maybe they're useful for proving concepts, but not for actual exploration. Maybe the real value is in learning what doesn't scale, so we can focus on approaches that might. Which brings us back to carrying fuel, not chemical fuel. We've established that's hopeless. Not even fusion fuel, which has its own problems. Something more exotic. Something that offers genuinely game-changing energy density. Antimatter. When matter and antimatter meet, they annihilate completely. Mass converts to energy with 100% efficiency. E equals mc squared with no losses. The energy density is unmatched by anything else in physics. A single gram of antimatter contains the explosive equivalent of several Hiroshima bombs. Use antimatter as rocket fuel, and suddenly the rocket equation becomes manageable. You can reach 50 to 80% of light speed with fuel ratios that, while still challenging, are at least theoretically achievable. You could send actual spacecraft, not nanocrafts, but vessels with meaningful payload capacity, across interstellar distances within human lifetimes. This is the dream fuel, the substance that makes interstellar travel possible without requiring revolutionary new physics. We know antimatter exists. We've created it in particle accelerators. We understand its properties. Using it for propulsion doesn't require theoretical breakthroughs, just engineering solutions. Except the engineering solutions are absurd. Producing antimatter is expensive, phenomenally expensive. Current methods cost about $62 trillion per gram. You'd need multiple grams for even a modest interstellar mission. The entire global economy couldn't afford the fuel for a single Starship. Production efficiency might improve. New techniques might reduce costs by orders of magnitude. But you're fighting against fundamental physics. Creating antimatter requires enormous amounts of energy because you're literally creating mass from energy. The process is inherently inefficient. You'll never get more energy out than you put in. Storage is equally problematic. Antimatter annihilates on contact with normal matter. You need containment systems that ensure zero contact. Magnetic bottles can theoretically hold antimatter indefinitely, but they require constant power. Any failure, any loss of containment, and your fuel supply detonates. A gram of antimatter, enormous explosion. Now imagine storing the kilograms needed for interstellar propulsion. You're essentially building a spacecraft around a barely contained superbomb. One malfunction away from catastrophic failure. The safety margins are non-existent. You can't have a minor containment breach. You can't have a partial failure. Everything works perfectly or everything explodes. There's no middle ground. Even if you solve production and storage, you still need to figure out how to actually use antimatter for propulsion. You can't just let it annihilate in a combustion chamber. The energy release is too violent. The temperatures are too extreme. You need ways to direct the annihilation, to channel the energy, to convert it into thrust without vaporizing your engine. Proposed designs use magnetic nozzles and plasma confinement. They look good on paper. None have been tested at scales beyond laboratory experiments. The gap between we can contain a few antiprotons and we can build an antimatter rocket engine is enormous. So antimatter propulsion remains firmly in the realm of theoretical possibilities, not impossible according to known physics, just impossibly difficult with known engineering. The kind of technology that's always a few decades away and likely to stay that way, which leaves us where? Light sails that only work for minimal masses, fusion that's still decades from working at all, let alone in compact spacecraft forms, antimatter that's theoretically perfect but practically impossible, chemical rockets that can't begin to approach the required velocities. Every propulsion option has a fatal flaw. Every approach hits a wall. Not the same wall, different problems for different technologies, but walls nonetheless. And these aren't problems that get solved through incremental improvement. They're fundamental limitations baked into the physics and economics of interstellar travel. You start to see why professional aerospace engineers don't spend much time on interstellar mission concepts. The problems aren't interesting from an engineering perspective. They're not challenges that yield to clever design or better materials. They're physics problems, math problems, the kind of obstacles that don't care how motivated or well-funded you are. The universe is structured in a way that makes interstellar travel extremely difficult for creatures like us, creatures that evolved on a planet's surface, creatures with limited lifespans, creatures that need specific environmental conditions to survive. The distances are too vast. The speeds required are too high. The energy needs are too extreme. Which raises an uncomfortable question. Maybe we're not supposed to reach other stars. That's the uncomfortable question sitting at the end of all this technical analysis. Maybe the universe is structured in a way that prevents biological life from spreading between star systems, not because of one specific barrier, but because of the cumulative weight of dozens of insurmountable problems. Think about what interstellar travel requires. You need propulsion systems that work at scales we've never achieved, energy sources that dwarf anything we've ever built, shielding materials that don't exist, life support systems that must function flawlessly for centuries, navigation accuracy measured in fractions of degrees across light years, communication systems that can transmit across distances where signals take years to arrive. Each problem is solvable in isolation, in theory, but you need to solve all of them simultaneously, in the same spacecraft, using technologies that must work perfectly because there's no rescue option once you're between stars. The Apollo program put humans on the moon. Incredible achievement. Required the focused effort of an entire nation and consumed roughly 4% of the federal budget at its peak. The mission duration was measured in days. The distance was close enough that radio signals arrived in under 2 seconds. Scale that up to interstellar travel. The mission duration goes from days to centuries. The distance increases by factors of billions. The complexity explodes exponentially. And you are asking humanity to commit resources for a project where nobody alive at launch will see the results, even if we solved every technical problem: propulsion, energy, shielding, life support. we'd still face the human problems. Who goes on a journey they'll never complete? How do you maintain social cohesion across generations in a closed environment? What happens when the crew decides they don't want to continue to an arbitrary destination chosen by long-dead planners? Generation ships sound romantic until you think through the details. You're asking people to spend their entire lives in a metal cylinder. Their children will do the same. Their grandchildren. Multiple generations living and dying without ever seeing Earth or the destination. The psychological challenges are staggering. Baseline estimates suggest each person requires 2 metric tons of consumables annually. Food, oxygen, water, other supplies. For 1,000 people over 250 years, you're looking at 500,000 metric tons just for basic survival. That's before you account for the ship's structure, propulsion systems, shielding, equipment, everything else. You need closed-loop life support that recycles everything with near-perfect efficiency. Any losses compound over centuries. A 1% annual loss rate seems trivial. Over 200 years, you've lost most of your resources. The margins are impossibly tight. Then there's the social structure problem. How do you govern a generation ship? What laws apply? Who enforces them? What happens during disputes? On Earth, dissatisfied people can leave. On a generation ship traveling between stars, there's nowhere to go. You're stuck with whoever else is aboard for your entire life. Historical isolated communities often develop strange social dynamics. Cults form, power structures calcify, genetic diversity decreases. Now imagine those dynamics playing out in a spacecraft where system failures mean death for everyone. The pressure would be immense. Some propose sending frozen embryos instead. Artificial wombs and robots raise the children upon arrival. Solves the generation ship problems. Creates entirely new ones. Who teaches the children? How do they learn their mission? What if the systems fail and wake them too early? What if they arrive and simply refuse to colonize? You're betting that technology developed before launch will still function centuries later, that nothing will break irreparably, that the AI systems will work as designed, that the children raised by machines will somehow become functional colonists. The failure modes are endless, and unlike Earth-based projects, there's no iteration, no learning from mistakes, no second chances. You launch and hope everything works because there's no mission control that can help. Even communication becomes a philosophical problem. A signal from Proxima Centauri takes 4 years to reach Earth. Question and answer takes 8 years minimum. You can't have a conversation. You can't troubleshoot problems. Every decision must be made independently by the crew or the spacecraft systems. As the ship travels further, communication delays stretch longer. By the time a message arrives, the situation that prompted it has evolved completely. The information is historical data, not useful guidance. The crew is truly alone in a way that's hard to comprehend. This isolation extends to knowledge as well. Science and technology continue advancing on Earth. New discoveries happen. Better methods develop. But the generation ship can't benefit. They're locked into whatever technology existed at launch. Meanwhile, centuries pass on Earth. By the time they arrive, everything they know might be obsolete. There's a depressing scenario called the weight calculation. It suggests that if technology improves fast enough, you should always wait to launch, because a ship launched in 50 years with better technology might arrive before a ship launched today with current technology. And a ship launched in 100 years might beat them both. This creates a paradox where the optimal strategy is to never launch. Always wait for better technology. Always assume the next generation will have superior capabilities. The logical conclusion is permanent delay. Of course, this assumes continuous technological progress, which isn't guaranteed, but it illustrates a real problem. Committing to interstellar travel with current technology means accepting that you're sending something primitive, something that better versions will surpass. Then there's the question of purpose. Why send humans to another star? What's the actual goal? Scientific exploration doesn't require humans. Robotic probes are cheaper, more durable, and don't care about the journey taking centuries. They don't need life support or social structures or psychological counseling. Send a small probe with good instruments. It can transmit data back. Mission accomplished. Colonization is the usual answer, establishing human presence on other worlds, ensuring species survival. Except Proxima Centauri probably doesn't have habitable planets. The star is a red dwarf. It's flare-prone. The planets in the habitable zone are likely tidally locked. One side always faces the star. One side always faces away. Not exactly Earth-like conditions. You'd need massive terraforming efforts, technology far beyond current capabilities. At which point, why not terraform Mars first, or Venus, or build rotating habitats in our own solar system? You get all the challenges of creating livable space without the impossible journey between stars. Species survival makes more sense. Don't put all humanity's eggs in one planetary basket, except nearby stars don't help much. A catastrophe that threatens Earth probably threatens the entire solar system. Rogue black hole. Nearby gamma ray burst. These threats operate on such scales that Proxima Centauri isn't far enough away to matter. Real species survival requires spreading across many star systems, dozens, hundreds. That way, no single catastrophe can eliminate humanity. But now, you're not talking about one impossible mission. You're talking about sustained interstellar colonization, waves of generation ships, infrastructure for launching them, resources to build them, all for a payoff that occurs thousands of years in the future. What civilization commits to that? What government funds it? What population supports it? The practical politics are absurd. You'd need global cooperation on scales never achieved, sustained funding across centuries, cultural continuity that maintains the mission as a priority despite changing circumstances, competing needs, and the simple fact that nobody alive will benefit. It's not going to happen. Not with current technology. Probably not with any plausible near-future technology. The obstacles aren't just technical. They're economic, political, social, and psychological, which brings us back to that uncomfortable question. Maybe we're not supposed to leave our solar system. The universe might be structured in a way that keeps species confined to their home systems. The distances are too vast. The speeds required are too high. The energy needs are too extreme. Not impossible in principle, just effectively impossible in practice. This would explain the Fermi paradox, the question of why we haven't detected alien civilizations, despite the vastness of the universe. If interstellar travel is this difficult for us, it's probably this difficult for everyone. Advanced civilizations might exist. They're just trapped in their home systems, the same way we're trapped in ours. Some argue that truly advanced civilizations would overcome these barriers. They'd develop technologies we can't imagine, physics we haven't discovered, methods that bypass the limitations we face. Maybe, but that's faith, not analysis. Based on what we actually know about physics, the barriers to interstellar travel aren't just engineering challenges. They're fundamental limitations. You're not fighting against insufficient technology. You're fighting against the structure of space-time itself. The speed of light isn't a suggestion. It's an absolute limit. Approaching it requires energy that scales to infinity. No amount of technological advancement changes that math. You can get more efficient. You can't break the fundamental rules, even if you imagine exotic solutions, warp drives, wormholes, whatever. They all require physics that doesn't exist. Negative mass, exotic matter, energy scales that dwarf anything in the observable universe. These aren't technologies we haven't invented yet. They're concepts that might be physically impossible. So where does that leave us? Confined to our solar system. Not forever, necessarily, but for any time frame that matters to current humanity. We might send probes eventually, small spacecraft pushed by lasers. They'd take decades to arrive. They'd transmit data back. We'd learn something about nearby star systems. That's probably the extent of realistic interstellar exploration, human travel to other stars. Not in our lifetimes, not in our grandchildren's lifetimes, possibly never with anything resembling current biology. We're creatures that evolved on a planet's surface. Our lifespans are measured in decades. Our bodies require specific conditions. The universe wasn't designed for us to move between stars. That's not pessimism, it's just physics. The distances are too vast, the speeds are too high, the energy requirements are too extreme. Every proposed solution hits fundamental barriers, not technical barriers, fundamental ones. And maybe that's okay. Our solar system contains resources beyond anything we've utilized. 8 planets, dozens of moons, asteroid belt, Kuiper belt, room for trillions of humans if we build rotating habitats, energy from the sun that dwarfs all of human civilization's needs. We could have an incredible future without ever leaving our stellar neighborhood, build massive space stations, terraform Mars, establish bases throughout the system, create civilizations in orbit, all without confronting the impossible physics of interstellar travel. The stars will remain distant points of light, beautiful, mysterious, forever out of reach. That conclusion feels almost comforting in a way. Stay home, build here, accept the boundaries. But there's something unsatisfying about it too. Something that nags at the human psyche. We're a species that crossed oceans not knowing what was on the other side, climbed mountains because they were there, went to the moon mostly to prove we could. Curiosity isn't just a trait we have, it's arguably the defining characteristic of our species. So the question becomes, even if it's impractical, even if it's nearly impossible, will we try anyway? History suggests yes. Humans do irrational things constantly. We attempt ventures with terrible odds. We pursue goals that make no economic sense. We explore simply because the alternative never knowing, feels worse than the risk. That drive has led to incredible achievements, also spectacular failures, sometimes both simultaneously. Consider the generation ship concept. It encapsulates both human ambition and human hubris perfectly. The idea is straightforward on paper. Build a massive spacecraft, put hundreds or thousands of people aboard, launch it toward a distant star at whatever speed you can manage. The original crew dies. Their children continue the mission. Eventually, generations later, descendants arrive at the destination. It sounds almost romantic, a multi-generational voyage across the cosmos. Except the practical problems are nightmarish. Start with the basic engineering. A generation ship needs to be enormous. You're not just supporting a crew for a few years. You need a closed ecosystem that can sustain hundreds of people for centuries. That means farms, water recycling, atmosphere management, waste processing. All of it has to work perfectly for hundreds of years with no resupply. No external help. No escape if something goes wrong. One major system failure could doom everyone aboard. And you're traveling for centuries. The probability of something critical breaking approaches certainty. Then there's the social engineering problem. Probably harder than the technical one. You're creating a closed society. These people never chose to be there. They were born into a mission their great-grandparents started. They'll die before reaching the destination. Their entire lives are defined by a choice made by people who are long dead. What happens when they decide they don't want to continue? When conflict arises? When social structures break down? There's no precedent for managing a completely isolated human population for centuries. Every society we've ever studied had contact with other groups, trade, migration, outside influence. A generation ship has none of that. Just the same people in the same confined space for hundreds of years. The psychological strain would be immense. Depression, conflict, possibly violence. You can't exactly call for help, can't evacuate, can't even go outside for a walk. And for what? So people hundreds of years in the future might reach a planet they've only seen in old data files. The motivation problem seems insurmountable. The original crew volunteers. They believe in the mission. But their great-great-grandchildren, they never signed up. They were simply born into this situation. Expecting them to maintain dedication to a mission they had no choice in seems optimistic at best. Yet despite all these problems, people keep designing generation ships, proposing them, studying them, because the alternative is accepting permanent isolation. There's another approach that sidesteps some of these issues. Cryogenic suspension. Freeze the crew. Wake them when you arrive. No need for a multi-generational society. No psychological strain from centuries aboard a ship. Except we can't do it. Not even close. We can freeze individual cells, small tissue samples. We cannot freeze a human and successfully revive them. The ice crystals that form during freezing shred cell membranes cause massive tissue damage. Current cryopreservation kills you. Some companies offer to freeze your body after death in hopes that future technology can revive you. That's not cryogenic suspension. That's wishful thinking packaged as a service. Real suspended animation would require preventing ice crystal formation entirely, replacing water in cells with cryoprotectants, cooling without freezing. We're decades at minimum from making that work, possibly it's impossible with organic tissue. So that leaves one more option. Don't send humans at all. Send something else. This is where the conversation gets genuinely interesting, because we're not bound by human limitations if humans aren't making the trip. Imagine a probe the size of a smartphone, weighs a few grams, powered by a light sail, a mirror that catches laser light from Earth and uses that for propulsion. You could potentially accelerate it to 20% of light speed. At that velocity, it reaches Proxima Centauri in about 20 years, sends back data, images, measurements. We learn about another star system without solving any of the impossible problems of human travel. This is the breakthrough Starshot concept, announced in 2016 by Yuri Milner and Stephen Hawking. Initial funding of $100 million. Goal: prove that laser-pushed nanocrafts could reach Alpha Centauri within a generation. It sounded revolutionary. Finally, a realistic path to interstellar exploration. Use existing physics. Miniaturize the payload. Push it with ground-based lasers. Simple, elegant, achievable. Except it's not going well. The project has gone quiet. Funding apparently stopped flowing. Scientists involved seem confused about its current status. Turns out, when your entire project depends on one billionaire's continued interest, things get precarious. But set aside the funding issues. Assume someone commits the money. Does the concept actually work? The engineering challenges are still enormous. You need to accelerate this tiny probe to 60,000 kilometers per second. That's ridiculous speed. The forces involved are immense. Any slight imperfection in the light sail tears it apart. Then there's targeting. You're aiming at a star system 4.25 light years away. The probe is moving at a fifth of light speed. Even a microscopic error in trajectory means missing the target by billions of kilometers, and you can't correct course. The probe has no fuel, no propulsion beyond the initial push. Communication presents another problem. The probe needs to send data back, over 4 light years, with a transmitter that masses a few grams. The signal would be incredibly faint by the time it reaches Earth. We'd need massive receivers to detect it. Plus, any data takes 4.25 years to get back. You launch the probe. 20 years later, it arrives. 4 more years before you see the first images. That's a 24-year round trip for information. An entire generation commits to a project they might not live to see succeed. But here's what makes this approach worth considering. It's actually possible. Not easy, not cheap, but within the realm of known physics. No warp drives required. No exotic matter. Just lasers, mirrors, and patience. If we're going to explore other star systems, this is probably how it happens. Small probes, moving fast, collecting data, sending it back. We learn about exoplanets, composition, atmospheres, maybe even biosignatures. That's not nothing. Actually, it's extraordinary. Confirming life exists elsewhere would fundamentally change human civilization. Even just detailed data about another star system would revolutionize astronomy. But it's not Star Trek. It's not establishing colonies, not making contact with alien civilizations, not any of the romantic visions that drive our imagination. It's robots sending pictures. That's the realistic ceiling for interstellar exploration. Unless something changes fundamentally. New physics, discoveries that overturn our understanding, breakthroughs that make the impossible possible. Science fiction loves this narrative. Some brilliant scientist discovers warp drive, or how to generate exotic matter, or how to create stable wormholes. Suddenly, the galaxy opens up. Humans spread across the stars. It makes for good stories. It's probably fantasy. Physics isn't arbitrary. The laws we've discovered work consistently across all observations, across all experiments, from particle accelerators to cosmic events. The math checks out. The predictions hold. Could we be wrong? Sure. Newton was mostly right. Einstein showed where Newton's laws break down. Maybe someone will show where Einstein's theories fail, but that doesn't mean anything goes. Einstein didn't make Newton wrong. He showed Newton's laws were approximations that work under specific conditions. The new theory explained more. It didn't throw out the old rules. It refined them. Any future theory has to explain everything current physics explains, plus more. It needs to match all existing observations while predicting new ones. That's an extraordinarily high bar. And even if such a theory exists, it doesn't guarantee faster than light travel becomes possible. More likely, we discover new physics that reveals why FTL is even more impossible than we thought. The pattern in physics isn't discovering that forbidden things are actually allowed. It's discovering that things we thought might be possible are actually forbidden. We thought perpetual motion machines might work. Physics forbids them. We thought perfect measurement was possible. Quantum mechanics says no. We thought simultaneity was universal. Relativity proved otherwise. The trend is toward discovering limitations, not loopholes. Expecting future physics to allow interstellar travel is betting against the historical pattern, which brings us full circle. The stars will probably remain distant, unreachable, at least for anything resembling current humans. Maybe that changes far in the future. Post-biological intelligence that doesn't need life support, minds uploaded to computers, consciousness transferred to machines that can endure centuries in space without issue. That's speculative, but it's at least theoretically grounded. If intelligence can exist in non-biological substrates, many problems disappear. No need for food, water, atmosphere. Radiation shielding becomes easier. Time becomes less relevant. A digital mind doesn't care if the journey takes 1,000 years. No psychological strain, no generational transition. Just patience and robust hardware. Is that even human anymore? Philosophically, maybe not. Practically, it might be the only way our civilization ever explores beyond the solar system. Not as flesh and blood, as information, but that's centuries away at minimum. Right now, we're still struggling with basic space travel within our own system. Mars remains incredibly difficult. The moon is expensive. Everything beyond that is exponentially harder. So the honest answer to when humans will reach another star is probably never. At least, not in any form we'd recognize. Not biological humans, not with current physics, not within any time frame that matters to living people. We'll likely send probes eventually, learn about nearby star systems remotely, discover whether life exists elsewhere. That knowledge alone would be transformative, but walking on planets orbiting other stars, building colonies light years from Earth, meeting alien civilizations, that's probably fiction. Beautiful, Inspiring fiction, but fiction nonetheless. The universe is structured in a way that keeps species isolated. Distance is too vast. Speed limits are too low. Energy requirements are too high. Not impossible in principle, just effectively impossible in practice. And maybe that's the real answer to the Fermi paradox. Not that aliens don't exist, but that nobody travels between stars. Advanced civilizations develop. They build incredible things within their home systems, but they never venture beyond because the physics doesn't allow it. The barriers aren't technological, they're fundamental. Every civilization hits the same wall, realizes the same truth, accepts the same limitation. The stars belong to whoever evolves around them, not to visitors from elsewhere. Each system develops independently, or doesn't develop at all, but remains isolated either way. That's not the story we want. We want connection, discovery, a universe filled with fellow travelers. Instead, we're likely alone in a very crowded galaxy, surrounded by civilizations we'll never meet, separated by distances that cannot be crossed. Human ambition runs straight into physical law, and physical law wins. Every time. That reality leaves us with one uncomfortable question. What do we do with this knowledge? Because accepting that the stars are unreachable changes everything. It reframes humanity's future. Our destiny isn't expansion across the galaxy. It's optimization within our cosmic neighborhood, making the most of what's accessible, which isn't nothing. Our solar system contains vast resources, asteroids full of metals, moons with water ice, energy from the sun beyond any conceivable need. We could build rotating habitats throughout the inner system, terraform Mars if we're ambitious, establish colonies in the asteroid belt, create floating cities in the clouds of Venus. None of that requires breaking physics, just engineering. Patient, methodical engineering over centuries. That's achievable, difficult, expensive, requiring coordination across generations, but possible with known technology and physics. Compare that to interstellar travel. One is hard, the other might be impossible. Yet culturally, we're obsessed with the impossible version. Science fiction primes us to expect galactic empires, star-hopping civilizations, humanity spreading across countless worlds. That narrative is deeply embedded. But what if it's fundamentally wrong? What if our future looks nothing like Star Trek? Instead of exploring strange new worlds, we perfect the one system we have. Instead of seeking out new life, we create it ourselves through genetic engineering. Instead of boldly going where no one has gone before, we build paradise in our own backyard. Is that disappointing? Maybe initially, but consider what we gain. Focus, resources that would vanish into impossible interstellar projects instead get directed toward solving actual problems. Climate change, resource scarcity, disease, death itself. Those are tractable challenges, difficult but not physically impossible. Throwing civilization's effort at reaching Proxima Centauri means not solving problems we actually can fix. That's a terrible trade, especially when the interstellar attempt probably fails anyway. There's also something beautiful about limitation. Scarcity forces creativity. Knowing we're confined to one star system means treating it carefully. No backup planet to escape to. No frontier to flee toward when we mess things up. Just this, our solar system, our only home, forever. That could drive a different kind of ambition. Not outward expansion, but inward perfection. Building sustainable systems, creating art and culture that lasts millennia, developing technologies that enhance life rather than just extending reach. Consider what advanced civilizations might actually do. If interstellar travel is impractical for everyone, advanced species likely focus inward too. Computational substrates, virtual realities, exploration of mathematical and philosophical spaces rather than physical ones. That might sound less exciting than starships, but it's potentially far richer. The space of possible experiences in virtual environments dwarfs physical exploration. Every conceivable reality could be simulated, explored, perfected. Why travel light years to find alien landscapes when you can generate infinite alien landscapes computationally? This might explain the Fermi paradox better than any other hypothesis. Advanced civilizations don't colonize galaxies because there's no reason to. Physical space is limiting. Virtual space is infinite. The real frontier is computational, not cosmic. So civilizations develop technology for a few thousand years, reach a certain threshold, then turn inward. They're still there, still active, just not bothering with the universe outside their home system. Too expensive, too slow, too pointless when better alternatives exist. That's simultaneously hopeful and isolating. Hopeful because it means the galaxy might be full of civilizations. We're just not detecting them because they're not expanding. They're at home, doing their own thing. Isolated because it means we'll never meet them. No galactic community, no sharing of knowledge across species. Just parallel development. Everyone evolving independently. Forever separated by the tyranny of distance. Some find that depressing. The idea that we're alone even in a crowded galaxy. But there's something honest about it. The universe doesn't owe us connection. It's not required to be convenient. Reality is what it is. Physics operates according to its own rules, not our preferences. We adapt to the universe, not the other way around. And maybe isolation isn't entirely bad. Look at Earth's history. Contact between civilizations often goes poorly. Colonization, disease, cultural destruction. Maybe the cosmic speed limit is protective. Each species develops in safety. No risk of being conquered by something from across the galaxy. No interstellar wars. No galaxy-spanning empires crushing younger civilizations. Just peaceful coexistence through enforced separation. Of course, that only matters if other civilizations exist. We still don't know if they do. The Fermi paradox cuts both ways. Maybe we're alone because interstellar travel is impossible. Or maybe we're alone because life itself is impossibly rare. The great filter might not be travel. It might be abiogenesis, or multicellularity, or intelligence, or technological civilization. Any of those steps could be so improbable that we're the only ones who made it this far, in which case the stars are empty. Not unreachable, just lifeless. That's a different kind of isolation, one where distance doesn't matter because there's nothing to reach anyway. Just barren worlds circling distant suns, waiting for someone to arrive who never will. That scenario is arguably worse. At least with impossible travel, we can imagine other civilizations existing, doing interesting things, just elsewhere. If we're truly alone, then the universe is a wasteland, beautiful but dead. Consciousness existing in one tiny corner, a cosmic accident that happened once and only once. We won't know which scenario is true for a long time, maybe centuries. Our ability to detect biosignatures is improving. James Webb can analyze exoplanet atmospheres. Future telescopes will do better. If we find oxygen and methane together on a distant world, that's probably life. If we find industrial pollutants, that's definitely intelligence. So far, nothing. But we've barely started looking. The search continues. Each null result narrows the possibilities. Each new world studied adds data. Eventually, we'll know. Until then, we're stuck with uncertainty, which might be appropriate. Humans aren't good with definitive answers anyway. We prefer mystery, questions without resolution. The stars provide that perfectly. They're there, visible, tantalizing, but forever out of reach. That creates permanent tension, desire without satisfaction. Maybe that's healthy, keeps us striving, imagining, wondering what could be out there even if we never touch it. And who knows, maybe we're wrong about everything. Physics has surprised us before. Quantum mechanics seemed impossible. Relativity contradicted intuition. Dark energy defied expectations. Perhaps some future discovery opens new possibilities, not warp drives or wormholes. Those still seem unlikely. But something we haven't imagined yet. Some loophole in the laws we think we understand. It's happened before. Could happen again. But betting on that is dangerous. Planning civilization's future around physics we don't have is irresponsible. We work with what we know, make decisions based on current understanding. If that changes, great. We adapt, but we don't sacrifice the present for a speculative future that probably won't arrive. So the practical answer remains unchanged. The stars are unreachable, at least for biological humans, at least with anything resembling current physics. We focus on what's possible, our solar system, our technology, our civilization. We build the best future we can within the constraints that exist, not the ones we wish existed. That's harder than it sounds. Humans are naturally aspirational. We want grand destinies, cosmic significance. Being confined to one star system feels small, but small is relative. Our solar system is incomprehensibly large by human standards. We could build millions of habitats, support trillions of people, create societies of breathtaking diversity and complexity, all without leaving the sun's gravitational influence. That's not small, it's vast, just not infinite. And maybe finite is better. Infinite possibilities are paralyzing. Finite possibilities force choices, priorities, focus. We can't do everything, so we do what matters most. That's not limitation, it's liberation. The emotional adjustment takes time. We grew up on stories of galactic exploration, Star Wars, Star Trek, endless frontier, infinite possibility. Reality is less accommodating, but reality also built the universe, created stars and planets, generated life and consciousness. That's miracle enough. We exist, we're aware. We understand physics well enough to recognize our limitations. That's extraordinary. Most matter doesn't do that. Most of the universe is inert, dead, unconscious. We're the exception. Temporary pockets of complexity in an ocean of entropy. That's precious, worth protecting, worth optimizing. So maybe the real question isn't, how do we reach the stars? Maybe it's, how do we make peace with not reaching them? How do we build meaning in a universe that's mostly inaccessible? How do we create purpose when cosmic expansion is off the table? Those are harder questions, less technical, more philosophical, but more important, because the physics isn't changing. The universe is what it is. We're the ones who need to adapt, mentally, emotionally, culturally. That adaptation is already starting, slowly, as evidence accumulates, as realization spreads. The stars aren't ours. They never were. They belong to whoever evolves around them. We get this system. That's our inheritance, our responsibility, our home. Human ambition doesn't die easily, though. Even accepting interstellar travel is impossible. We'll keep pushing, sending probes, gathering data, learning what we can from a distance. That's valuable. Knowledge for its own sake. Understanding the universe, even if we can't touch most of it. Science doesn't require colonization, just observation, measurement, theory. We can do that from here. Map exoplanets, study stellar evolution, detect biosignatures if they exist, build a complete picture of cosmic ecology without ever leaving home. That's still ambitious, still meaningful, just different from what we imagined. And maybe someday, thousands of years from now, someone figures something out. Some trick we missed, some technology we couldn't imagine, post-biological intelligence with capabilities we can't predict. Maybe they solve it. Maybe they reach the stars. But that's their story, not ours. We're biological humans in the 21st century. We work with what we have, build what we can, accept what we can't. That's not defeat, it's wisdom. Recognizing reality, working within it, making the most of what's actually possible rather than mourning what isn't. The stars will always be there, distant, beautiful, unreachable, reminding us that the universe is larger than our ambitions, older than our species, indifferent to our desires. We don't get everything we want. Nobody does. We get what physics allows, what reality permits, what effort and ingenuity can achieve within actual constraints. For humanity, that means one star, one system, one chance to build something lasting, not across the galaxy. Right here, that reframing takes effort, generations of effort, cultural evolution. Stories need rewriting, dreams need reimagining, ambitions need redirecting. Not toward impossible stars, toward possible futures within reach. That work starts now, with us, the generation that sees the evidence, understands the constraints, accepts the boundaries, and chooses to move forward anyway within actual limits. Some will resist. Denial runs deep when dreams die. They'll point to historical breakthroughs, claim impossibilities became possible, argue we just need more time, more technology, more innovation. They're wrong. This isn't like heavier than air flight, not like breaking the sound barrier. Those challenged engineering, not physics. The difference matters. Engineering problems have solutions. Physics problems have limits. We're facing physics. Hard boundaries built into reality's structure. No amount of clever design changes that. Others will retreat into fantasy. Warp drives, wormholes, exotic matter, convenient plot devices that let stories ignore constraints. Fiction serves purposes, entertainment, inspiration, exploration of ideas. But fiction isn't roadmap. It's imagination unconstrained by reality. We live in reality. Reality has rules. Those rules don't bend because we wish they would. The universe isn't obligated to accommodate human ambition. It just is what it is. We're the ones who adapt or fail. Still others will find this liberating. Constraints focus attention. Limited resources force priorities. Impossible goals waste energy better spent elsewhere. If stars are unreachable, stop reaching. Start building. Transform this system. Make it everything it could be. That's ambitious enough for millennia. More than enough to occupy human ingenuity indefinitely. We don't need infinite frontier. We need meaningful work, purpose, progress, all achievable right here. Consider what's possible within one star system. We've barely started. Mars remains untouched, Venus unexplored, Europa's ocean unprobed, Titan's seas unvisited, hundreds of other worlds waiting, asteroid belt full of resources, Kuiper belt mysteries, Oort cloud unknowns, decades of exploration available without leaving Sol's gravity well, centuries of development potential, millennia of optimization possibilities. Space habitats offer another avenue. O'Neill cylinders, Stanford Tauri, rotating structures creating artificial gravity, entire ecosystems in manufactured environments, populations in millions, resources from asteroids, energy from the sun, independence from planetary surfaces, not dependent on finding habitable worlds elsewhere. Build habitation wherever raw materials exist. That's achievable with known physics, known engineering. Just requires scale, effort, time, terraforming presence, long-term projects. Mars could support atmosphere. Venus might cool eventually. Engineering on planetary scales, timeframes measured in centuries, but possible within physics constraints. No exotic matter required, no faster-than-light travel needed. Just patient application of known principles. Massive undertaking. Worthy challenge for civilization that accepts its boundaries. Even Earth needs work. Climate management, ecosystem restoration, sustainable systems, population distribution, energy transition. Problems requiring solutions we haven't implemented. Why dream of distant stars when home needs attention? Fix what's broken here, optimize what works, build what's missing, then expand outward gradually within reach. The solar system contains everything needed for thriving civilization. Energy from fusion eventually, materials from asteroids, space in orbital habitats, exploration on nearby worlds, research in unique environments, development of new technologies, creation of art and culture. All the ingredients for meaningful existence. Just requires accepting. This is our sandbox, playing within it, making it work. That acceptance doesn't mean stagnation. Progress continues, just directed locally. Solar system development is frontier enough. Challenges aplenty. Problems to solve, discoveries to make. Not across galaxy. Right here, in our cosmic backyard, where physics allows actual achievement rather than theoretical dreaming. Some technologies improve life here. Fusion power changes energy equation. Closed-loop ecosystems enable space habitats. Advanced materials strengthen structures. Artificial intelligence assists management. Genetic engineering adapts biology. Nanotechnology manipulates matter. None require leaving solar system. All benefit from focused development here. That's where investment belongs, where effort pays dividends, where progress happens. Scientific understanding continues advancing too. Telescopes improve constantly, detecting exoplanets, analyzing atmospheres, searching for biosignatures, mapping cosmic structure, understanding stellar evolution, learning universe's history, all from safe distance. Observation doesn't require visitation. Knowledge doesn't demand presence. We study distant phenomena without traveling there. That's sufficient for science. Understanding doesn't need contact. Maybe someday something changes. Unlikely, but possible. Physics occasionally surprises. New theories emerge. Old assumptions collapse. Revolutionary insights occur? Rarely. But history shows it happens. Relativity replaced Newton. Quantum mechanics revealed atomic reality. Perhaps something else waits undiscovered. Some principle we missed. Some loophole in constraints. Improbable, not impossible. If that happens, future generations benefit. Not us, not our children. Maybe not for millennia. Fundamental physics advances slowly. Decades between breakthroughs. Centuries between revolutions. Any solution to interstellar travel problem lives far in future. Beyond prediction. Beyond planning. Beyond current relevance. So we work with what we know. Build what's possible. Leave speculation to distant descendants. Meanwhile, we face practical questions. How do we structure civilization around single star? What does long-term planning look like? What goals make sense for species confined to one system? These aren't technical questions. They're philosophical, cultural, existential. Harder than engineering. More important than technology. Because mindset matters. Attitude shapes behavior. Collective belief drives civilization direction. Current space culture still assumes expansion, colonization, spreading across galaxy. That narrative needs updating. Not abandoning, redirecting. Same energy, same ambition, different target. Instead of reaching stars, fill system. Instead of crossing light years, optimize local space. Instead of finding new worlds, build artificial ones. Same drive, realistic goals. Education systems need adjusting too. Stop teaching interstellar colonization as inevitable. Start emphasizing solar system development as priority. Show students what's achievable. Give them problems they can actually solve. Inspire with real possibilities rather than impossible dreams. That's not limiting imagination. It's directing it productively toward the goals that matter, within constraints that exist. Media representation matters. Science fiction shapes expectations. When every story involves galaxy-spanning civilizations, people expect that's our future. It's not. Stories need updating. Show thriving solar system civilizations. Explore challenges of limited space. Address questions of sustainable existence. That's fertile ground for storytelling, just different from traditional space opera. More realistic, more relevant. Economic planning changes too. Interstellar ventures aren't coming. Stop allocating resources toward them. Redirect investment to solar system infrastructure, orbital facilities, planetary research, asteroid mining, fusion development, technologies with actual payoff. That maximizes return, benefits current and near-future generations, rather than spending on impossibilities. Political structures adapt. No galactic government needed, just solar system coordination. Still complex. Multiple worlds, numerous habitats, diverse populations, but manageable scale. Communication delays measured in hours, not years. Travel times in weeks, not generations. Governance remains feasible. Democracy survives. Human connection persists. Within one system. That's advantage of limitation. The psychological adjustment is hardest. Humans like thinking big, dreaming impossible dreams, reaching beyond grasp. That's beautiful quality, drives progress, but needs grounding in reality. Otherwise, wastes energy on futility. The trick is redirecting ambition toward achievable greatness rather than impossible fantasy. Solar system development is achievement enough. Building thriving multi-world civilization is accomplishment worthy of species that dreams of stars. Just accomplished here. There's dignity in acceptance, wisdom in recognizing limits, maturity in working within them. Childish ambition demands everything. Adult responsibility optimizes available. We're growing up as species, leaving childhood fantasies, embracing adult realities. That's progress, different from imagined, still meaningful. And meaning is what matters. Not scope, not scale, not distance covered, but significance achieved, impact made, value created. That happens locally, in communities, among people. Between worlds we can actually reach. Meaning doesn't require galaxy, just consciousness, connection, purpose, all available within one star system. So this is our lot. One star, 8 planets, countless smaller bodies, vast space between, all the room we get, all the frontier we have. It's enough, more than enough. It's home, not stepping stone, final destination, the place we make work, where we build everything worth building, where human story unfolds, complete, contained, ours. The stars remain distant, beautiful, untouchable, reminding us the universe is bigger than our reach, older than our species, indifferent to our dreams. We don't get everything we want. We get what physics permits. That's one system. Make it count. That's not limitation. That's mission. Clear, achievable, meaningful. Right here. Looking at all this, you might expect a neat summary. 5 bullet points. Key takeaways. Lessons learned. But that's not how this ends. Because there isn't really an ending. Just a continuation of the same reality we started with. The stars are still there, still unreachable. That hasn't changed, won't change. Not in your lifetime, probably not ever for biological humans. And you know what? Maybe that's the most honest conclusion possible. No twist, no silver lining. No, but wait, here's hope. Just physics, mathematics, reality doing what it does regardless of what we'd prefer. Every technical barrier we examined is real. The distances aren't getting shorter. Light speed isn't negotiable. The rocket equation doesn't care about human ambition. Energy requirements don't decrease because we really want them to. These aren't problems waiting for solutions. They're features of the universe we inhabit, permanent characteristics, like gravity, like time, like the fact that nothing lasts forever. Some people hear this and feel defeated, like humanity failed somehow, came up short, didn't measure up to science fiction's promises. That's backwards thinking. We didn't fail. The universe just works differently than stories suggested. Fiction serves its purpose: entertainment, inspiration, thought experiments. But it's not blueprint, not prediction, just imagination exploring possibilities. Reality operates on different terms, harder terms, less accommodating to narrative convenience. The universe wasn't designed for our satisfaction. It simply exists according to its own rules. We're the ones who showed up late and started making demands. Other species probably face identical limitations. If they exist, if they've developed technology, if they've looked up at their own skies and wondered about reaching other stars, they've hit the same walls, learned the same lessons, accepted the same boundaries. That's actually comforting in a strange way. Not humanity-specific failure, universal constraint. Everyone gets one star system. Use it or waste it. Those are the options. Nobody's colonizing galaxies. Nobody's building empires across light years, because nobody can. Unless physics changes, which it won't. Or unless someone discovers loopholes that probably don't exist. Or unless post-biological intelligence solves problems biological life can't. Maybe, eventually, thousands of years from now. That's someone else's story, though, not ours. We're here now, this century, this civilization, with these constraints, working with actual physics, building with available materials, reaching for achievable goals. That's not settling, that's realism. And realistic goals within our solar system are still staggering. Mars alone represents decades of challenges. Venus is mystery waiting. Europa's ocean beckons. Titan's seas intrigue. Hundreds of worlds within reach. Actual reach. Not theoretical, not impossible. Just difficult, expensive, requiring patience and coordination, but doable. Then there's space itself. Not empty void. Potential construction zone. Rotating habitats. Artificial gravity. Manufactured ecosystems. Populations in millions. Resources from asteroids. Energy from sun. Independence from planetary surfaces. All achievable with known physics and developing technology. That's not consolation prize. That's incredible opportunity. More than any previous generation could imagine. More than we'll fully utilize for centuries. Frontier enough for species that accepts its boundaries and works within them. The psychological shift is real, though. Requires letting go of galactic destiny narrative, accepting smaller stage, finding meaning in local achievement rather than cosmic expansion. That's cultural evolution. Takes time, generations probably, not happening overnight. Current generation bridges two worldviews. Grew up with Star Trek, living through reality check, watching impossible dreams hit immovable physics. That's uncomfortable position, but necessary one. Someone has to see clearly, accept honestly, redirect appropriately. Future generations will have it easier. They'll grow up knowing the constraints, never expecting galactic expansion, focused on solar system development from start. That's advantage of adjusted expectations. Energy directed productively rather than wasted on fantasy. The stars won't disappear. They'll remain visible, beautiful, inspiring, just not destinations. More like distant mountains you admire but never climb. Part of landscape, not journey endpoint. That shift in perception matters. You can appreciate beauty without possessing it. Marvel at distance without crossing it. Wonder about possibilities without experiencing them. That's maturity. Sophisticated relationship with reality. Adult acceptance of what is rather than childish demand for what isn't. Science continues regardless. Telescopes improve. Detection methods advance. We'll learn about exoplanets, study their atmospheres, search for biosignatures, map stellar evolution, understand cosmic ecology. All from here. Safe distance. Observation without visitation. That's sufficient for knowledge. Understanding doesn't require presence. Maybe we find life elsewhere. Probably we do eventually. Statistics suggest it exists. Whether we detect it depends on various factors. But if we do, what then? Radio contact, maybe. If they have technology. If they're broadcasting. If signals survive the distance. 8-year conversation delays minimum. Longer for most stars. No back and forth. just messages into void, hoping for response, waiting decades. That's not relationship. That's cosmic pen pals. Interesting, not transformative. Or we find biosignatures, oxygen and methane on distant world. Proof life exists elsewhere. That's huge scientifically, philosophically, changes how we see ourselves. But practically, doesn't affect much. Life exists. We can't reach it. They can't reach us. Everyone stays home. Knowledge increases. Nothing else changes. Even finding intelligent signals doesn't enable meeting. Just confirms we're not alone, and that we're all isolated, scattered across galaxy, separated by distances that make communication difficult and travel impossible. That's reality of cosmic community, aware of each other, unable to interact meaningfully. Some find that depressing. Galaxy full of civilizations that never meet, never collaborate, never share beyond radio signals, forever alone together. But depression requires expectation. If you never expected galactic civilization, isolation isn't disappointing. Just how things are, and maybe it's protective. History shows contact often goes badly. Colonization, exploitation, disease, cultural destruction. Maybe cosmic speed limit is safety feature. Keeps civilizations separated, prevents stronger from dominating weaker, allows independent development. Everyone gets their own space, protected by physics itself. That's optimistic interpretation. Equally possible, there's nothing out there. We're alone. Only consciousness in dead universe. That's heavier burden. Makes our isolation absolute. Not just unable to visit neighbors. No neighbors to visit, just us. Temporary awareness in cosmic void. We won't know for a long time. Maybe ever. The search continues. Data accumulates. Each null result narrows possibilities. Each discovery adds information. Eventually, picture clarifies. Until then, uncertainty, which humans handle poorly, but must accept anyway. Back to us though. Our species, our civilization, our solar system, our actual situation, not hypothetical aliens, not theoretical futures, just what's real, what's now, what's achievable. One star, that's the deal. Not punishment, not limitation, just physics. Same physics that created everything. Built stars, formed planets, generated life, enabled consciousness. That physics gives us this system, this opportunity, this chance. Make it count or waste it. Only options available. No do-overs. No backup planets in other systems. This is it. Our one shot. Our only home. Forever. That focus could drive incredible achievement or squander into nothing. Depends on choices made. Resources allocated. Priorities set. Energy directed. All within our control. Unlike physics. Unlike cosmic distances. Unlike light speed barriers. Those are given. These are chosen. Choose wisely. Build carefully. Think long-term. Act deliberately. Within actual constraints. Toward achievable goals. That's not settling. That's wisdom. Working with reality as it exists. Not as we wish it were. The stars will watch. Silent, distant, unreachable. Reminding us the universe is larger than our ambitions. Older than our species. Indifferent to our desires. They'll be there long after we're gone. Unmoved by our brief existence. Unimpressed by our accomplishments. Just burning. Just existing. Just being stars. And we'll be here. In this system. on these worlds, in these orbits, building what we can, learning what we're able, living how we choose, within the boundaries physics provides. That's not small achievement. That's everything possible, which is enough. Has to be, because it's all we get. So that's it. No triumphant ending, no breakthrough revelation, no hope for future travel. Just acknowledgement of limits, acceptance of constraints, recognition that some dreams don't come true. Not because we failed, because universe works differently than we imagined. The next star sits 4.25 light years away, right where it's always been, right where it will always be, forever beyond our reach, forever beyond anyone's reach, protected by distance, guarded by physics, isolated by reality itself. And that's okay. Has to be. Because wanting something impossible doesn't make it possible, just makes you want. Better to want what's achievable, build what's realistic, accomplish what's available within one star system. Our star system, our only home, here, now.